Good evening, students. Yesterday we have completed the chapter that is chemical kinetics, and today we will move to inorganic. Okay. So, the first chapter that we'll be dealing today is said as classification and periodicity of elements. So, in this chapter, basically, we will cover the whole topic, that is, all the topics that are in this JEE syllabus in one day only, because it is a short chapter, and say you can consider it as a easier chapter also. So, basically, in this chapter, we will just classify the elements that are present naturally in the environment as per the modern law. Okay, so let us see what is the modern law and all. So before this Henry Moseley, many of the scientists have used different type of classification methods for classifying the elements, but I think those are not that much important and according to the JEE syllabus. The latest one that was designed by this Henry Moseley, which is as said that the all the periodic properties of an element are the more described by its atomic number rather than its atomic mass. So this was the Henry Moseley modern law. Now, what are the consequences of this law? We will see how this made the newly formed periodic table. So, before that, let us see the some crucial points of this Henry Moseley law. So, it said that atomic number is a more fundamental property of an element than its atomic mass. Okay, so this should be clear. So, before this Henry Moseley, one more scientist has say classified this elements using this atomic mass. But later on, it was seen that atomic number, which is that equals to the number of protons present in an element, is more basic to the say finding the properties of that element. Now, using this fundamental property, that is atomic number, they classified the elements. Now, why is this modern periodic table, or you can say periodic table, is important? Why is it necessary to classify elements? Because there are a numerous number or complex number of elements present in the environment. Now we cannot study each of them individually. So to classify them, the aim is that so that we can study a set of those, and suppose we have five elements in the set, and we can consider that all have the almost equivalent chemical property and physical property. So this is the main reason behind the classification of elements, so that we can easily study the physical and chemical properties of this numerous number of say elements that are present in the nature. Now later on many more elements are added. So up till now, according to this book, a 118 elements are present. Now for the many more elements were added, but we will not consider them. Okay, so let us move to this chapter. So in this table we have, which the in which we will see image of this in later slide. Elements are arranged in increasing order of atomic number, which means that the least number of protons, means the element which is having the least number of proton is placed on the top, and then accordingly we change this say position of the elements according to its atomic number. Now the isotopes, these are grouped in the same. So suppose an element has two isotopes, then it doesn't mean that it will be represented two times in a periodic table. So each isotope has suppose an element A has three isotopes, so it will be given one position only, which will be allotted to all of those isotopes. So it is not an important point, but you should keep in mind in this. Okay, now later on, the table consists of, if you just look at the structure of the table, it has 7 periods that goes from left to right and all, and 18 groups. Okay, from up to down, and the concept of subgroup A and B is removed. Okay, so this is a more you can say complex way of representing this modern periodic table, which has this subgroup of A and B, but now it has been removed. Okay, so let us see this table. So this is the table we have of the modern periodic table. So I should advise you that you should remember this table whole, because not whole, at least you should remember up till the transition element. I will make you remember what is this transition element and all, but you should at least remember up till transition element, because uh, questions are asked from there, and you need to classify these properties and all using those atomic number. So many tricks are available. I'm not mentioning them here. You can refer to any say teacher, or you can say site for this tricks, and you should remember their atomic number at least up to the transition metal elements. You can say up till groups 5 to 6, you can say you should be aware about this atomic number. So if you look at this periodic table, we have 7 periods that are 1, 2, 3, 4, 5, 6 and 7. So it's starting from here, we have 7 periods. So it goes from left to right like this. And then we have this group, that is 1, 2, 3, 4, 5, 6 and all. Now you can see very clearly that earlier it was 1A, 2A, 3A and all. So it is what divided into subgroup A and B, but it was later on dropped off, and then we have this only 1, 2, 3, 4 and all. Now if you see here, this hydrogen element is not placed anywhere but in the center. So due to the it has a peculiar nature, you can say it does not have a place in periodic table. Still it is looking for one. So you must be thinking that why in periodic table we see that okay, hydrogen is placed here, but in reality this hydrogen still does not have its place that is regularized. Okay, but we keep this here for formality, that is here, because it has some properties like it should be metal but it is a non-metal, you know very well. Now due to this all reasons it is having a contradictory say position in the periodic table. Now we will see how this are divided into S, P, D and F. So you must have heard this thing that S block elements, P block elements, which are together named as the main group. Then we have the P block, and sorry, the D and F, which are called the transition and inner transition elements respectively. So we will see all this. So regarding this inner transition element, so I'm now just giving a glimpse of it. So you can see here two rows are placed down that are of lanthanoids and actinoids. Okay, now, if you see here, we are going from 57 to 72, and between this 57 and 72, some of the elements are missing, which are placed in the downward fashion. So, it was placed here, which are called the lanthanoids and the actinoids, and they are called the inner transition metal. The same goes for 89 to say 103. Okay, so you must remember this, that which is the starting point or the atomic number for this lanthanides or actinoids, that is 58 to 71 for lanthanoid and 90 to 103 for actinoid. Okay, now let us move to the classification of this SP and DF and see how this electronic configuration helps in say distributing this elements. Okay, so first we will start with the S block elements. So what is the general configuration for S block elements? It has an unfilled s orbital. Okay, so this is an s, you know that s has maximum number of 2 electrons, so ns goes from 1 to 2. So if an element has an unfilled s orbital, then it is called as s block element. Okay, now in s block element we can have two groups, that is 1 and 2, because we know very well that ns1 and ns2, these are only two possibilities. Okay, so if it is ns1, then we will call it as alkali. Okay, and if it is ns2, we will call it as alkaline. So if you look here, you can see, so this is the group of alkali metals that we have here, that is lithium, sodium, potassium, rubidium and all, and these are the alkaline metal. Okay, now let us move to another, that is p block elements. So p block elements goes from 13 to 18. Okay, so you can see here that we have this 13, 14, 15, 16, 17 and 18. So including this noble gas and halogen and all, the P group is made, so the P block is meant here. Okay, now if you look at this general configuration, it goes as like NS2, NP1 to 6. So we can have NS2, NP1, NS2, NP2. Similarly, we can have it up till NS2, NP6. So it can have 6, okay, 1, 2, 3, 4, 5, 6. So in this way, we can classify it as the P block. Now this whole S and P block as a whole is called the main group chemistry. So you must have heard this term in JEE also in the syllabus, that okay, this is main group elements and these are transition elements. So we group this S and P block in one name, under one name, that is called as say we have this main group elements. Now it goes from 13 to 18 excluding helium. Now this should crucial point here, you should keep in mind this, that we do not include helium here. So if you look at this table that is placed here, you can see very clearly that it has an ns2 configuration. So it is not a p block, because in p block element the p orbital should be the last or the valence shell, but it is not so. So you can just exclude this helium. Okay. Now let us move to this D block. So same thing written here also, that S and P block elements are known as the main group elements. Now, before moving to this, say D and F block, let us see what is diagonal relationship. So we will later on see the physical and chemical properties of this S block elements and P block elements D and F and all. But before this, let us make a clear clarification that there is still some kind of relationship of between this, say, which are not in the same group also. But by which I mean to say that it is generally found that elements of the same group have almost same properties of, that is of, say, either you say the physical properties or the chemical properties, but there is an exception in that. That is, we can see that if we are having this second group, second period, that is lithium, beryllium, boron, carbon, and if we compare it with the third period, that is sodium, magnesium, aluminum, and silicon, then in general, one should say that okay, so these are in the same group, so that should have the same properties, but it is not so. Okay, so this is not the general case, and we know very well that chemistry is a game of exceptions. So if you see here, if you observe the chemical and physical properties, it can be clearly seen that it has a diagonal relationship kind of behavior, okay, or phenomena. So lithium and magnesium share the same type properties. Similarly, beryllium and aluminium share the same type of properties. The same goes for boron to silicon. Okay, so this should be kept in mind. It's a very important concept. Questions are often asked from this diagonal relationship. Okay, so the same thing is written here. The first three elements of the second period shows diagonal similarity with the element magnesium, aluminum, silicon of the third period. Okay. Now, if you want to generalize it, it is said generally that the first group of every S and P block element has a diagonal relationship with its consecutive period. So that should be a, you can say, a general statement that should be made, that first group of every first S and P block element has a diagonal relationship with its next down consecutive period. Okay. Now let us move to this D, or you can say transition element. So sorry for this mistake, it is OR. Okay, so D block or transition metal elements. Now transition metal elements are more complex compared to this S and P block because of the involvement of the D block, D orbital. So you will see why it is crucial. So when we will study about this D block elements, D and F block, then we will also see coordination. A whole, you can say, a branch of chemistry has evolved due to this involvement of this D block element or the coordination chemistry. So due to this involvement of this D orbital, so it is a result of this D orbital. So D orbital is very, you can say, complex to study thing. You can say that. Okay. Now, what are the group that are considered in it? It is goes from third to 12th number. Okay. So it goes from third to 12th number, and the general configuration, if you want to consider, it goes from n minus 1, D1 to 10, ns1 2. So this is the general configuration of it. Now there is an exception in this, so let us see those exception. So if you want a more generalized, say, definition of this transition element, then it should have means an incomplete orbital distribution in its oxidation state also. Means you have to consider the oxidation state also, like the zinc example we have. So it has a completely filled d orbital, but in its some oxidation state like Zn plus or Zn2 plus, it has an incomplete d orbital occupation. So if you look at the periodic table here, the zinc is placed here, so you can see very clearly that okay, so this, it is completely filled, but if you just oxidize it, that is remove one electron from it, then it will show a incomplete d orbital. Okay, so due to this reason, this zinc, cadmium, and mercury are all included in this transition element. Okay, so that should be kept in mind. Now let us move to our next slide. So this is the last classification we have. So this says about F block and inner transition element. So why is it inner transition element? Because you can see very clearly that we have taken a part of the transition element and put it in a different period. Okay, so in the downward it is placed. Now what is the general configuration for it? So you must remember at least the general configuration of each and every group. Say it is S, say it is P or D or F. You should remember this general configuration, which goes as n minus 2 F14, 1 to 14, n minus 1 D to 0, 1, 2, and ns2. Now we have this F block involvement. Okay, now this involvement of this F orbital in this lanthanide and octanide has very significant effects on its atomic radius and all. So we will see all those in the coming slides. The thing which is called the lanthanide and contraction and the octanide contraction. So it mainly happens due to this poor shielding effect of F orbital. So we'll see it later. Because I'm saying this all because we have studied this shielding effect in the first chapter also. So mainly it depends upon the shape of the orbital, but that how diffused it is. Means the more the diffuse the orbital, the more it will be showing, the less it will be showing the shielding effect. And S orbital is said to have the least diffused shape, and F is in the opposite, or you can say on the opposite side of this line. Now we have this two series that is called 4F for lanthanoid and 5F for actinoids, and they're also called as rare earth element. Okay, so if you consider F block from modern point of view, then it is a very broad. It has a very broad scope of research. Okay, so many research have been going on this F block element. So that must be topic for another day. I'm just giving you a say idea that why we are studying this chapter. Okay. Now, before moving to the physical and chemical properties, let us start and see how is nomenclature in this inorganic compound done. So, in general, we do not have a nomenclature for the inorganic compound, but for the element greater than 100, we do have a nomenclature. So, it's very easy. Sometimes questions are asked from JEE, you can just directly attempt it in a minute or half, and you can secure marks very easily. So, you must study this topics. You can because it requires very little efforts and give you a number that should be of a greater worth. Okay, so how it is done? So let us see. So we have a unique code that is related to each and every number. Say it is 0, we have nil. Then for 1 it is un, bi, tri, quad, pent, hex, sept, oct, and n. So you have the same, or you can say a similar type of coding for this organic also. We have bi, tri, quad, pent, hex, sept, oct, and n. Now, how do we name this or how do we say, name this compound after 100? So, suppose we have a compound named as 101 having an atomic number of 101. Then, how we will classify it? We will do simply is what? We will take the code of 1, which is un. Then, for 0, we have nil. Then, for 1, we have un. Now, we will place these three things together and put IUM at the last. That's all. That is the root we have. Okay. So you have to do nothing. Say we have another example like 1 103 1 2 3, or you can say. Then for 1 we know it is un. For 2 we have bi. For 3 we have tri. So we will set it as un, bi, tri. So in this way you can just add the root name plus each and every digit has its code. Now you can just name this element very easily. Okay, so this is a very silly thing to remember, but yes, it can be of importance of some time. If it is asked in the exam, you can just directly secure marks. Now let us see some of the physical properties or the physical traits that are observed in the periodic table. Now we will start with the very simple, that is atomic radius. But it is, what is atomic radius? It is the distance between the nucleus to the outermost shell. So in simpler terms, you can say it that yes, it is the distance between the outermost shell and the nucleus. Now what are the trends it follows? So on moving to left to right in a period, atomic radii decreases. Okay, so if you move from left to right in a period, so if you see the periodic table, so this is the periodic table we have here. So if you move from this side to this side, okay, so if you move from this side to this side, then the atomic radii decreases. So why does it happen? So let me explain it for you. Okay, so if you consider the attraction between this electron and the proton, It is just a electrostatic force of attraction that is existing between these two. Okay, so this is clear for all. You must have studied this. Now what happens due to this? So as we are increasing the number of electron on the outermost shell, so when we move from a period from a left to right, we know very well that we are adding electron in the outermost shell. Now due to this addition, this electrostatic force of attraction increases. Why? Because we know that electrostatic force of attraction is directly proportional to this um, product of the charges. So the charge is increasing one by one. Now due to this reason, as we move from left to right, we see a size contraction, means the size contracts as we move from left to right. Okay, so this is a general trend. So all the trends that we will talk about now is a general trend. So there are many more, say we have exceptions, but we will not look at those. We will just see the general trends for now. Then we will, if we have time, then we will look for the exceptions and all. Now if you move from group 1 to down, so if you are moving down the group, let me show you. If we move from down the group here, if you move down the group, the number of shells that will be adding upon one by one. So if you consider lithium, it will have two shells, then three shells, then four shells, and so on. So as we're moving down, we can clearly see that the number of shells is increasing. And due to this reason, we are having an increase in size as we move from top to bottom in a group. So I will just generalize all this concept in one figure that is given in NCRT. It should be easier to remember that. But for now, just we are seeing the reasons behind it. Okay. Now let us see a graph. So it is a graph of atomic radii across the atomic number. So we can see very clearly for a period that we are moving from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So as we are moving left to right in a period, the atomic radii is decreasing one by one. So it is decreasing. Okay. So lithium, then boron, then okay. So suppose that sign will have. So it will be lithium, then boron, carbon, nitrogen, and then oxygen, and then fluorine. Okay. So this is the order of this. Similarly, if we look at this period, sorry, the group, then you can clearly see here that we have lithium, then we have sodium, then we have potassium, we have rubidium and cesium. Same, so this is for the alkali metal. Now for alkaline metal, we can see that, so this is not for, this is for halogen, fluorine, chlorine, bromine, then iodine. So this is the periodic trend for the atomic radius. Now let us move to some kinds of atomic radius. The first one we have here is for covalent radius. So what is covalent radius? So if you consider it for a diatomic molecule, so suppose you have a diatomic molecule that is a homodiatomic molecule like nitrogen and hydrogen molecule. Now if you consider the distance between their centers, then the half of it is called as the covalent radius. So we'll see this thing pictorially also through a schematic diagram, but for now you can consider as it as the distance between or the bond length between the two covalently bonded atoms divided by 2. That is the covalent radius. Now similarly, if we have this for heteroatomic, okay, then the bond length will be Ra plus Rb. So Ra and Rb are the covalent radius of A and B. Then chi A and chi B are the electronegativities of A and B. Okay. Now it is defined in a different way. Now what will be this, say DAB, that is the distance bond of between the A and B. It will be Ra. Okay, so Rb then minus 0.09 electronegativity of A minus electronegativity of B. So this is the new formula. You can just keep it in your mind. So this is nothing but homonuclear distance for Ra divided by 2. This is for B divided by 2. Then we have this electronegativity. So you have heard this term electronegativity earlier also. If not, I will mention and describe it in a brief on the upcoming slides. Okay, so this is for heteroatomic, diatomic molecule. Now let us move to this atomic radius for the metals. So for metals, it is very simple. So we know that metal will always exist as a lattice, and the distance between this lattice ions divided by 2 gives us the metallic radius. Okay, so this is a simple formula. We will not focus on this more. Now the thing that is to be kept in mind is that R dash is greater than actual size of atom. Okay, so this should be kept in mind that this metallic radius is greater than this actual size of atoms. Why? We will see it later. Then we have this van der Waal radius. So you must have heard this van der Waal force and all. So it is the distance between the nucleus of identical two non-bonded isolated atoms. So what is it? We will see it. Okay, so what is this? It is the distance between the nucleus of identical two non-bonded isolated atom. So we will see it through a schematic diagram. So just remember this say statement. Okay. Now R1 is much more greater than the actual size of atom. So this is the thing. Now if you consider general trend, it is given as the largest is the smallest is the covalent radius, which is the distance between the two covalently bonded molecule divided by 2, and we have the metallic radius, which is the distance between the lattice ions divided by 2, then the van der Waal radius, which is the distance between two non-bonded isolated atom, okay, divided by 2. So this is the difference. Now the thing that should be kept in mind is that at the end of the periodic table, atomic radii of inert gases are exceptionally large because they do not form molecule and their radii are simple van der Waal radii. So we know very well that there would be no metallic radii or no covalent radii for this, say, uh, noble gases, because they do not form any bond as they're inert in nature. So there are exceptions down the group, but for now it is well known that they do not form any bond. For that case, we take the van der Waal radii of this inert gases, and for that case atomic radii is very large for this inert gases. Okay, now let us move to the diagram that is describing well this van der Waal radius and all. So if you look here, so this is the covalent radii. So this is the distance between the center of the two atoms. Okay. Now, if you divide it by 2, then you will get the covalent radius. Now, if you compare this covalent radius with this atomic van der Waal radius, it will be like this. So, in covalent radius, we are just seeing the distance between the two covalently bonded molecule. Okay, but in van der Waal radius, we are seeing the distance between the two isolated atoms. So I have said it earlier. Remember the definition. So this is the these two are isolated from each other. They are not bonded to each other. So we will see the distance between this to this, and then we will half it and get our van der Waal radius. Now why it is so large? You can see here that after having a sphere like this area covered, it has an additional area that is covered by this molecule. This is the thing. Okay, let me delete it. Yeah. So this is the extra area like this. So the upcoming molecule do not cross this area because of the electrostatic repulsion. So of course, an molecule is made up of electron cloud and proton, but since proton is centered at the nucleus or the center, due to this reason it has a electron cloud surrounding this proton. Now electron cloud of this plus electron cloud of this always repel each other, so they do not approach as close as these two can do. Okay, so due to this reason there is a larger gap between these two, and the distance between these two isolated atoms is considered as the 2 of the van der Waal radius, 2 times of the van der Waal radius. Now you can see very clearly that the covalent radius for this molecule is 99 picometer, on the same molecule as the van der Waal radius of 180. So it is almost double times. Okay, so generally it is said that it is having a certain this kind of, so if you see it, it has a 2.38 kind of relation between these two. We will see that relation also. So let us move to this ionic radii. So similarly, we have this covalent radii, we have also this ionic radii. So it is the distance of the outermost shell of an ion from its nucleus. So it is very simple to remember. It is the distance of an ion from its nucleus to the outermost shell, that is the ionic radii. Now cationic radii is always get smaller than its neutral atom. Now this should be kept in mind. So what is the logic behind is this? Say we have an element, okay. Now it loses some electron. Okay, now after it loses cationic, after it loses electron, there is a greater number of proton that is present. Okay, now due to this greater number of proton and the fewer number of electron, they will experience a greater charge or a greater electrostatic force of attraction. Okay, so due to this reason, this contracts, the cation contracts, and it has a smaller size than neutral atom. Similarly, in case of anion, if we add electron, so this is anionic radii, sorry for this. Okay, so this is anionic radii, these two are together. So if you consider an anionic radii, we know very well that an anion is formed upon addition of electron. Now the number of proton is not that much as compared to the number of electron. It is a chemical imbalance or a neutrality imbalance. At the same time, there is nothing to balance the means energy. There is a repulsion between the upcoming electron and the and the existing electron. Now due to this reason, the shell expands from its neutral size or from its default size. Due to this reason, anions have a larger size. So you should remember this thing that, okay, so this is important point I am making here, that cations have the smaller size, then comes the neutral atom, and then comes the anion. So this is the trend of ionic radii. So you should keep this in mind. Okay. Now let us consider an example here. So O22 minus has the greatest size. Then we have the O minus and the O. Similarly, if I have a hypothetical situation having O plus, it will have the smallest. Then we'll have the O2 plus. Now, if we write it for isoelectronic species, then we can say that ionic radii is inversely proportional to the magnitude of nuclear charges. Now, what is isoelectronic species? So, isoelectronic species are those that are having the same number of electrons. So, those are called the isoelectronic species. Now, let us move to the next physical property, which is called as ionization enthalpy. So, what is this ionization enthalpy? So, it is the energy required to remove the electron from the valence shell. So, in that simple sense, you can say, and the means atoms which are considering whose shell is to be considered to remove the electron, that should be in the gaseous cation. Okay, so that should be kept in mind that we are removing an electron from a gaseous atom and we convert it into a gaseous cation. So this is an important point I am making here. So suppose an enthalpy change is given regarding a reaction which is changing a gaseous atom into gaseous cation, that then only then it is a ionization enthalpy. In case if we are converting say a liquid atom into a gaseous atom, that is also a liquid, so we will not consider it as the ionization enthalpy until and unless both the reactant, that is the atom to be converted, and the atom that is formed are in the gaseous state. So that then and then only the energy that is involved in it is called it as ionization enthalpy. Now from generally left to right, the ionization enthalpy decreases. And why is it so? So as we move from left to right, we know that the atomic radii is decreasing. Now since the atomic radii is decreasing, the electrons are moving more closer to the proton, or you can say the positive charge. Now if we have to remove an electron, we have to apply a greater amount of energy that is must counterbalance the force that is applied by the proton to this say electron. Okay, so this should be kept in mind. But there are some exceptions, like if we have half filled orbital or fully filled orbital, then it has a high ionization energy. So it should be kept in mind. So if you have a general example, you can consider the noble gas, which has a complete electronic configuration and a full filled orbital. So they have a extra hype when we move from this halogen to this say noble gas, then it's an extra hype in the ionization enthalpy, and this is mainly due to this full filled orbital or the complete octane, because fulfilled orbital and half filled orbital are very stable due to this Holtz multiplicity. Okay, now what are the factors that affect this ionization energy? The first and the foremost is atomic size. Second is eye screening effect, so you will see this training effect very in depth after this. Then the nuclear charge. So suppose something is having a negative nuclear charge, so something is having a negative charge, then the ionization enthalpy of this will be always and always greater than a neutral atom, and will be smaller than the will be greater than this. Sorry, this will be opposite sign. So ionization enthalpy of this will be greater than we have this. Okay, so ionization enthalpy. So if you consider ionization enthalpy, it is generally, or you can say it is always positive in nature, we because we do have to apply energy as we are removing electrons from it. Okay, so ionization enthalpy is positive in nature. So this has the greatest ionization enthalpy. Then we have this, then we have this. So why is it having the greatest ionization enthalpy? Because we know very well that it is having a positive charge. Already it is electroneutral neutrality balance is different. Okay, default, and now you are trying to impose or trying to remove an extra electron. Okay, so this will require a large amount of energy as compared to the oxygen. While O negative has a negative charge, so it should be easy to remove that because it will revert back its electroneutrality. Now, if you see this trend here, so this is the graph. So as we move from lithium to beryllium to boron, then from carbon, nitrogen to oxygen, we can see that boron has an extra hype here, and similarly nitrogen has an extra hype here. Why is it so? So if you look at the electronic configuration of both of this, let me draw its electronic configuration. So we know very well that nitrogen is 7, so it will be 2, 2, and then 3. Now if you see here, you can see very clearly that it is a half filled orbital or p orbital, half filled p orbital. Now this half filled p orbital is giving an extra stability to this nitrogen 7. Now due to this reason, it is difficult to remove the electron from nitrogen as compared to oxygen. Due to this reason, we see a hype in this electron gain ionization enthalpy of this nitrogen. Now similarly, if you look for beryllium, we know very well that hydrogen, helium, then lithium, then beryllium, then it goes from 1, 2, 3, 4. So if you write the electronic configuration, it will be like this. So you can see very clearly that it is having a full filled orbital. Okay, so this will be unfilled, sorry, 2s2 and 2 1s2 and 2s2. So it is a full filled orbital. Due to this reason, we have this extra stability of this helium atom. Therefore, we require more energy as compared to the upcoming atoms, that is boron and all. Okay, now if we see this here, we are having a general trend. So we are moving from lithium to sodium, potassium, rubidium. So as the atomic radii is decreasing, the ionization enthalpy is also increasing. The ionization enthalpy is also decreasing because we know it has an inverse relation with the atomic radii. Now let us move to some exceptions. So helium has the highest ionization enthalpy, and you know very well because it has the smallest size, and plus it has this. So it has not the smallest size as compared to this hydrogen. It is larger, but due to its completely filled octet, so it has a completely filled octet. It is very difficult to remove an electron from this helium, so it is very stable. Now cesium has the lowest one because as you see the periodic table, it is placed at the bottom. You can see very clearly it is placed at the bottom here. Now since it is placed at the bottom, it has a larger size of course, and now if you remove one electron, it will go to its most stable state, which is a complete octet. Now due to these two reasons, it has a greater ionization enthalpy, sorry, smaller ionization enthalpy. So that's why it is also used for this photoelectric effect. So you must have, if you have seen this atomic structure lecture, must have seen that I have used cesium as the metal for electropositive because it is the most electropositive and the least ionization enthalpy. Why? Because of the larger size, and after removing one electron, it will have the stable configuration. Now, one more thing, ionization values of this inert gases are exceptionally high. You know the reason because it has a complete octet. And while alkali metal have the lowest ionization energy of all. So, if you look at the left side of this periodic table, you can see very well that it has only one electron that should be removed, and after that it will go to a stable electronic configuration. Due to this reason, this elements have this smallest ionization enthalpy as compared to other groups like alkaline metals or transitional metals or p block elements. Okay, now if we move to this group 2 element, now group 2 element is greater than corresponding elements of the group 13 due to their full filled s orbital. Okay, now this is the exception. You can see here that the ionization energy of group 2 elements, okay, So the ionization energy of group 2 elements. So if you look at the electronic configuration of group 2 elements, it will have a complete. So this, if this is ns2, this is the valence electron we have here, that is ns2. So every element of this group 2 element, every group 2 element, that is alkaline metals, have this complete octet. Now due to this complete octet, it is very difficult. Complete octet not means a full filled orbital, a full filled orbital. Now due to this full filled orbital, it has a greater ionization enthalpy as compared to this 13 element. So 13 have not such means stability due to which is means provided to group 2 elements of its field as orbital. Okay, so this should be kept in mind. Now the effective nuclear charge will be less than the actual charge on the nucleus. Now we see the shielding effect. So what is shielding effect? We'll see it. So let us move to the shielding effect. Now before that we should know that what is this Z effective. Now if you consider an atom here, then suppose we consider an atom here. Okay, so it will have a nucleus, then it will have a shell, and again it will have a shell. Now there will be consecutive more shells. Now this shell that is present in the outermost is experiencing some kind of repulsion, or you can say shielding from this inner core shells. Now due to this reason, the Z effective that should be experienced, or the Z actual that should be experienced by this shell, decreases due to the shielding effect of the inner core cells. Okay, so this is called the shielding effect. And what is Z effective? It is given by Z minus sigma, where sigma is the shielding constant. So we'll now see that how this shielding constant is calculated. So it has some general rules. You should just keep in mind all of those. Then you will be able to calculate this Z effective. So before calculating this shielding effect, first of all we have to write this in this order. Why I'm telling this? Because we know that we are writing as 1s2, 2s2, 2p6, 3s2, 3p, then we are writing 4s. Now we'll not write it in such order. We will just first of all, then second we will 2s and 2p in one, 3s 3p in one, then 3d in one, 4s 4p in one, 4d in one. So in this way you will arrange it first of all. Okay, after rearranging it according to this configuration, means you can see here that we are putting first of S together, then S and P together, then D alone, and then F alone, and we are not keeping this 4S here because of the energy reasons. We are just putting it in the last. So first we will see the numbers, then we will see S and B together, then D alone and F alone. Now we will see why we are doing it so. Identify the electron of interest. So you will not be told always to calculate it for valence electron. Suppose you can be told to calculate it for this, to calculate it for this. Then in that case, you will not consider this remaining one. So all this will be boycotted if you are calculating the shielding effect on this, or the Z effective for this 2p, because shielding effect, there is no shielding effect from the outer core orbitals. Okay, so this should be kept in mind. Now how will calculate it? Now, if the shielding effect is experienced by an S and P electron, that it has a rule. It says that electron within the same group, that is, suppose we have this 1s, 1s2, and okay, so let us consider other example 2s2 and 2p6. Okay, now we know that they are in the same group. Now, if you are told now to calculate, okay, so calculate it for 2s2, 2s electrons, then you will consider all the electrons of this except that one. So we will have 7 electrons in total that will be in the same group except this 2s. Okay, now if we are considering it for the 1s, then the shielding effect will be 0.30, and except that there will be 0.35. So what I mean to say here that, so if we are considering an electron that is 1s2, and you are set to calculate the shielding effect of this one. Okay, now in that case 1s electrons, then you will take the contribution of the other electron as 0.30 and not 0.35. Okay, so I will give you example, it will make more clear. Now electron within the n minus 1 group, now suppose the group is ns2, sorry, 2s2 and 2p6. Then if you have to consider for n minus 1, then it will be 1s. So the 1s electron will give a contribution of 0.85, and the remaining n minus 2 and lower will give a contribution of 1. Okay, so this is the general rule for S and P. Now, if you are considering the shielding effect that is present in D or F, though they both have the same rule, so electron within the same group experiences 0.35, and the remaining one gives a 1. Now, let us take an example. Okay, so suppose we have this configuration that is 1s2, 2s2, 2p6, so they will be the same group. Then we have the 3s2, 3p3. Okay, now if we calculate this constant, that is sigma, for the 3p3, then we will calculate it as, so 3p3, this group has 5 electrons, but we have to calculate for the 1 electron, so we will remove all, we will take other than that, as if 4 into 0.35. Then moving to the inward group, we have this 8 electrons, so it will give us as 0. So let me see it, what was the contribution? So its contribution was 0.85. Okay, so sigma will be equals to 1s2, 2s2, 2p6. Okay, then we have 3s2, then we have 3p6, 3p3, sorry, and then we have to calculate the sigma, so we'll calculate it as 1s2, so we have this 3 electrons here, 4 electrons here, so we'll multiply this 4 by 0.35. Okay, now similarly 0.35. Okay, now the remaining electrons are 6 and 8, so 6 to 8, 8 are here, so it will be 0.85. 0.85. Now the remaining are 1s2, so it will be simply 2 into 1. You will just add this and you will get the value of sigma. Okay, so if we have this 1s2, or sorry, say we have sp group. Okay, now if the case is different, okay, so let me make a different case here for you. Suppose we have this filled 3p6 and then we have the 3d. Okay, so we will have a different kind of contribution for that. So 3d5, so 4 into 0.30. Okay, and the remaining all, that is 8 8 plus 2 10, will have a 1, and you will add this all and you will get an answer. So this is the sigma for it. And what is the Z effective? Z effective is given by, Z effective is given by atomic number. So that is the atomic number that we have here, that is Z minus sigma, that is this one. Okay, so this is the thing here. Now let us move to this electron gain enthalpy. So what is this electron gain enthalpy? It is the energy released when an electron is added to an isolated gaseous atom. So here also we are taking an isolated gaseous atom. So always and always for ionization energy, or say we have this um, say we have this electron gain enthalpy, we will use gaseous atom and then we will make a gaseous ion or an ion or cation out of this gaseous atom. Okay, now what is electron gain enthalpy trend? So as we move from across the period, it decreases, it increases, and we, as we move down the group, it decreases. So we know the reason. So since we have to add one electron, the distance between the electron and the nucleus, a valence electron and the nucleus, goes on increasing as we move down the group. So we have to say it will have a greater affinity to attract that electron as compared to the electron means atom which is in the having the smaller size. Similarly, as it goes across the period, its size goes on decreasing. So the element that is present on the left side, on the foremost left side, will have a greater tendency to attract the electron. Now chlorine has the highest electron affinity, and fluorine has the highest oxidizing power. So why is it so? So let us look at this. So if you consider the periodic table here, that is this thing, you must say that okay, fluorine has the smallest size, so it should have the greatest electron gain enthalpy. But there is an exception in that. Why? Because to the smaller size of the fluorine. Now fluorine has a very small size, it has no 3s orbital and all. Now as we add electron, there is a kind of repulsion between this electron. Due to the small size, there is kind of repulsion that is coming from the inner electron. So it is very difficult to give the electron to fluorine. At the same time, it has an electron affinity very greater due to the least distance between the electron and the nucleus. So it has a greater oxidizing power. So this point should be kept in mind that although that fluorine has the greatest oxidizing power, chlorine has the greatest electron gain enthalpy. Okay. Now let us look some factors. So very obvious, atomic size varies inversely. Okay. Nuclear charge varies indirectly. Then we have the configuration. So as we add electron to this half filled or full filled, it is difficult to do so. At the same time, if we are adding electron and that atom is having a half filled or a full filled, after adding that electron, then it will have a greater electron gain enthalpy as compared to the previous one. Now this electron gain enthalpy is also called as, so before moving to the next slide, let me make me a point, is called as the electron affinity. So it is a different term that is used. What is the difference between electron gain enthalpy and electron affinity? Just the difference between and the sign. So suppose electron gain enthalpy is x, then electron affinity will be minus x. So that's the only difference between this electron gain enthalpy and electron affinity. You should keep this in mind because many times electron affinity term is used in place of electron gain enthalpy. Okay, so fluorine and oxygen atom is the small size and great high charge density, therefore they have lower electron gain enthalpy. So I said earlier also the same case goes for oxygen also. Okay, now electron gain enthalpy of group 2 elements and 15 is low because of the stable half filled configuration. So for the same reason we have this say higher ionization energy, it has a low electron gain enthalpy. Okay, so this is the reason we know that half filled and full filled orbital are more stable as compared to the other. Now next move to the next thing. It is a tendency of an atom to attract the shared pair of electron. Okay, so what is this electron negativity? So this is the last physical trend that we will see. Okay, that is electronegativity. So what is this? It is the you can say the tendency of an electron, the tendency of an atom to attract an electron. It is not a measure, you can say it is not a thermodynamic property, it is just a tendency. So fluorine, it is the first in this, so it has the greatest ionization electronegativity. Okay, so you should keep this in mind. Then we have the chlorine, oxygen, then chlorine, then nitrogen, bromine, and all. So this three is very important, you should keep this in mind. It not only help in predicting this electronegativity, it will also help to predict the dipole moment. So if you know the electronegativity of this element, then you can say that if I had the common cation, say we have the H attached to all of this, then in that case you can easily predict the dipole moment, because we know very well that dipole moment is directly proportional to the charges. It is the uh, product of the charges and the distance. So if it adds a greater electronegativity, then there will be a greater separation of charge and we will get a greater dipole moment. Okay, now in period we know very well, as we move from left to right, the electronegativity increases. For the same reasons we have the ionization enthalpy in all. Then in group, if you move down the group, then the electronegativity decreases. Okay, now this has some value, so we call it tendency, but we do want to measure it. We do want to say that okay, this is the value of electronegativity. So for that reason, two Mulliken and Pauling have given some scale. So Pauling scale is simple, it says that electronegativity of A minus electronegativity of B is equals to the 1.012 in root delta, where delta is the bond energy minus energy for 100% covalent bond. So we'll see what is it. So it is this, given as energy as A minus AB as the dissociation enthalpy of AB in kilocalorie per mole. And how we'll calculate this delta? It will be EAB minus root under this EA into EB, that is for EA and this is for B. So suppose we have a molecule that is AB, then if you want to calculate this say electronegativity, then according to Pauling scale, chi A minus chi B will be equals to this we have this 0.102 root under delta, where delta is equals to the dissociation enthalpy of AB minus root under dissociation enthalpy of A into dissociation enthalpy of BB. Okay, so this is the reason. Now we have this Mulliken scale. So let me make a point here that generally Pauling scale is more popular than this electronegativity scale. So this scale is more popular than the Mulliken scale. But you should remember this also, because it is in a syllabus and it will it can be asked in exam. So the question is that we have to calculate the electronegativity using this ionization energy and electron gain enthalpy, or you can say electron affinity. So here it is electron affinity, not electron gain enthalpy. So you have known very well it is a negative of electron gain enthalpy. So it is ionization energy plus electron affinity divided by 2. Now, what is the relation between this molecular scale and this Pauling scale? So, molecular scale is almost 2.8 times greater than the Pauling scale. Okay, so this is the relation between these two. Now, this is the we can say Pauling scale is this. Okay, so this is the final formula. So, there is the relation between the chi m and chi p, that is electronegativity according to Pauling and electronegativity according to Mulliken. Now let us see some more points about the electronegativity. So unit of electronegativity is electron volt, and for noble gases its value is taken as 0. We know very well that a noble gas has a complete octet, so it will have a no affinity for the gain of electron. Okay, so it will not have any value of electronegativity. Now sp hybridized orbital is more stable, more electronegative. Why? Because we know very well that in sp we have a greater S character. So if you have not studied this covalent bonding and all, but if you want to know that why this sp is having this greater electronegativity, then we have sp2 than sp3. So sp has a 50% S character and 50% p character. Now to do this reason, we know that S orbital is more electronegative because it is more penetrated toward the nucleus because of its spherical size and less diffuse shape. Now, due to this reason, it has a greater S character, and greater S character means greater electronegativity. So this has a greater S electronegativity compared to this one, which has a 33.33% S character, and the remaining has 66.66 S character. Now we have sp3, which is 25% S character and 75% P character. Now you can see very clearly that we have an increasing S character as we move from 3 to 2 to 1, and same goes for electronegativity. Now let us summarize all of these properties in one diagram that is given from taken from NCRT. So let us summarize it. So as we move from top to bottom, electronegativity increases, and from left to right, electronegativity also increases. Okay. So you should remember this as a whole. That can easily help you to remember all the properties. Now if you see here the relation between atomic radius and all, so as the atomic radius increases, electronegativity decreases. Okay, and ionization enthalpy decreases, electron gain enthalpy also decreases, and all these properties, three properties, electron gain enthalpy, ionization enthalpy, electron gain enthalpy, are inversely proportional to this atomic radius. Similarly, atomic radius is same, it goes for the period also. Now if you look at the metallic character, then metallic character decreases as we move from right to left across a period, and increases as we move from left to right, sorry, right to left here. Okay, sorry for the mistake. So I am saying that as we move from left to right, then the metallic character decreases and the non-metallic character increases, and vice versa. Okay. Now let us look at the valency. The valency of an element is related to the electronic configuration. We know very well that we can just say the valency of this element using the electronic configuration. So say we have this element that is NaH, CH2 and LH3. So we know very well that it is plus 1. It has a plus 1, minus 1, plus 1, minus 2 and all. So it is just a general idea about valency. You know about valency very well. So I'm not going to describe it very well. Okay. But valency of the element with respect to oxygen increases from 7 along a period. Okay. So I'm just passing on this slide. Just look at this. So the main thing is in the later slides. All elements in a group have the same valency. Yeah, this is an important point that should be made. That all elements in a group have the same valency. So if you look at the group, okay, so if you look at the group, if you form the hydrides of all of this, okay, so if you form the hydrides from all of this, then it will be simply LiH, NaH, AH, RBH and all. So you can see that all have a valency of 1. Okay, so and this is also ns1. So the valency and the outermost configuration are same. Okay. Now, if you look at the p block element, the valency on count of the inert pair effect. So what is the inert pair effect? We will describe it very briefly in the chemical bonding. So for now, just remember this term. Now, term oxidation state is also used for this covalency, which indicates the actual charge on the atom in that particular atom. So if you have a molecule, say we have this CaO, okay, so the oxidation number of Ca is +2, or you can say the covalence is also +2, and oxygen has a oxidation state of -2. Now, let us see some exceptions. So tin has a maximum number of isotopes, so 10 in number. Osmium has the highest oxidation state, that is +8. Okay, so keep this in mind. So oxidation has the highest oxidation state of +8. Now transition metal in so variable oxidation state. So we will see why this D block element, C and F block element shows a variable oxidation state. It is so because they have an involvement of D block elements. Okay. Now let us see the chemical reactivity. Now the reactivity of metal increases with the decrease in ionization energy. Why? Because as the ionization energy decreases, it is easier to remove the electron and they react very easily. On the contrary part, reactivity of non-metal increases with the increase in electronegativity because it will easily attract the upcoming electrons of the coming metal and then we will form the bond. Now on moving left down the group, the reactivity of metal increases and for the non-metal it decreases because we know the electronegativity is going in the same way. Now the reducing character of the elements increases down the group. Why? Because what is reducing character? So reducing character means it is oxidizing very easily. So how it will oxidize? Then it will lose its electron, that is smaller ionization enthalpy. And we know very well that as we move down the group, the atomic radius is increasing and the electrostatic attraction is decreasing. Now it is easy to remove the electrons, so it will be oxidized easily and we will have a greater oxidizing power, and same is the case for oxidizing character. Okay, now if you look at the alkali metal, so they are the most reactive one, and that reactive that if you keep sodium metal in open, then it will simply react with oxygen and catch fire because it has a very low ionization enthalpy. The electron can move very easily from it and it can easily form bonds with the element. Okay, now halogen has the most reactive strongest oxidizing agent. Why? Because it can easily attain the noble gas configuration just by taking one electron. So it easily take the electron and get reduced and oxidize the other. Now let us make some points on the basicity. So metal forms basic oxide and non-metal from acidic oxide, and basic in state of the oxide and hydroxide decreases down the group and acidic nature of oxide increases along the group. So you can explain it with the help of Lewis base character, Lewis acid and base. So we know very well that species which you can say gives takes electron are called acids and which gives electron are called bases. Okay, so on that basis you can explain this basicity and basicity of this metal oxides and non-metal oxides. Now almost all metal oxides are basic in nature except this Al2O3. Why? Because Al2O3 is somewhat covalent in character. So it shows some covalent character. Due to this reason it is amphoteric. So amphoteric means it can act both as an acid and base. So same is the case for ZNO. Similarly, non-metal oxide like CO, N2O, NO are neutral, while CO2O7 is the most acidic oxide. So it is a important point. You should remember this. Okay. Now we'll move to some questions. So I will solve some 5 questions, then you will solve it by yourself. Okay. The ionic radii of N3 minus, F2 minus, and F minus are what? So you do not have to remember the value. You just have to compare these three values. So let us see how we'll solve it. So these three are isoelectronic species. We know very well because if you consider the nitrogen, it has 7 electrons. So three are removed. We are left with 4. So oxygen has, sorry, we are added 3 electrons, so it will be 10. Now oxygen has 8, will be 10. It has 9, it will be 10. So all these have 3 electrons. Now for isoelectronic species, we know very well that ionic radii is dependent upon this nuclear charge and it is inversely proportional. Now since the charge is increasing on this, the electrostatic force is decreasing, and we see a trend that is N3 minus at the largest size, then we have the O2 minus, then we have the F minus. So this is the case. Okay, so we will just assign the values accordingly. Now the correct sequence of ionic radii is, now we know very well that as the cationic charge increases, the size of the atom get reduced. So if first we have to find that whether all of these are isoelectronic or not. Okay, so we will refer this both alongside other. So if you see here, then O2 minus will have the greatest size. Why? Because it has is an anion. Then with the F minus, then we have this L3 plus, and then Mg2 plus, and all. Okay, so we'll let us see the solution. So O2 minus, then F minus, then Na plus, Mg2 plus, and Al3 plus at the smallest size. For the similar reason, that is increase of electrostatic attraction due to decreasing number of electron and all. Okay. Now the element which of the following outer electron configuration may exhibit the largest number of oxidation state. Now oxidation state is variable in case of d orbital, when we know very well that this variable oxidation state is mainly shown by this transition metal element. So those who have completed the syllabus may know this, but we will see in the transition metal elements or D and F block element as well. So this 3D5 will show the variable configuration because it exhibits the largest number of oxidation state. Now mixture containing this aqueous solution are electrolyzed. Cation are discharged at the cathode in the order. So cation are discharged means they are releasing the electron. So this is the equation for that. So which will easily form this. Okay. So let us see. It will be decided on the base of the size. We know very well that the potassium has the largest size, so it will take the electron least easily. Then comes the sodium, then comes the lithium. Okay, so this is the order. Let us see the solution. So this is the ionic radii. So this is the thing. Okay, okay. So this is the long solution that I put here. So let me do it for you. The cations are discharged at cathode. So potassium has the largest size. So this will have this greatest, smallest ionization energy. Okay, so this will be the order. So this is the wrong solution. Sorry for that thing. Now this is the last question today I will solve. After that, you will just see the questions of 6, 7, 8, 9, 10, and then we will end this lecture. So in which of the following arrangement the order is not according to the property indicated by it? So increasing metallic radius, we know the trend. I have given you the graph in one, or you can say I give you a schematic diagram, and you can just refer to it and solve all of this problem very easily. Okay, so let us see. So it is very true because we know that we are moving down the group, so the metallic character will increase. Electron gain enthalpy of chlorine is more. This is exception I have told you earlier. So this is also true. Now ionization enthalpy of nitrogen is greater. Should be greater. This thus it is incorrect. And why it is greater? Because it has a half filled orbital. Nitrogen has a half filled orbital. Now I will just show this all these questions and you will just solve by it yourself. Okay. So this is 6 number question. Then we have 7 number. Okay, so just can just take the screenshots if you want. 8 number is ninth. Okay, and this is the 10th. So thank you for today's time. So now we can end this lecture here. We have completed this chemical periodicity. Okay, thank you.